In our previous lesson, we discussed types of physical quantities where we stressed very much on vector quantities and scalar quantities. So if you have not watched that lesson, quickly watch it and come back to this lesson. You must have remembered that we mentioned force as an example of a vector quantity. So in this lesson, we'll be focusing very much on resolution of vectors. And the examples we'll be using force and momentum as the vectors that will be resolving. For resolution of vectors, yes, you might be new to it, but by the end of this lesson, we will try our best to make it as simple and understandable as we possibly can. Good. But before we look at resolution of vectors, what it actually means, I want to throw a little light on how to represent forces using diagrams. During representation of forces using diagram, we use straight lines to represent forces. The length of the line tells you the size of the force or the magnitude of the force. So for example, if we say 10 Newton force, represent it this way with this line, 10 Newton force with this length, then maybe 20 Newton force will be somewhere like this. So the length of the line tells us the magnitude of the force. And then on that line you'll be drawing, there will be an arrow on the line. The size of the arrow tells you the direction in which the force is being applied. So if I draw a line and an arrow is pointing in a particular direction, that tells you the direction of the force. Good. So I think that makes sense to you. Now, what exactly is resolution of vectors? So listen to this definition or meaning of resolution of vectors. Resolution of vectors means splitting one vector into two perpendicular components that have the same overall effect as the original. So let me explain that. Resolution of vectors. When we say vectors, we are simply referring to vector quantities. Good. Quantities with size and direction. What do we mean by resolving or resolution of vectors? It simply means that you've been given one vector quantity, just one. That one vector quantity, you split it into two perpendicular vectors, such that at the end, the overall effect of those two lines or vectors will be equal to the effect of the original. Let me explain using this scenario. Suppose you have a ball. So the ball has a starting point. Then the ball has been kicked down to a new location. Now you can see that there's one smooth movement of the ball from this original location to the new location. But I know you would agree with me that this ball can also be moved from the starting point to this same location using two steps. You can first move it from the top to the down and from the down to this location. So that means the overall effect of moving from here to down and from the down to this side has the same effect as moving from the top straight to this end. So the original force that was applied on the ball is this inclined one. That's the original. So when you are given the original, you have been asked to resolve it. It means split this original into steps that have the same overall effect as the original. I think that makes sense. If it doesn't make sense, then you can leave it in the comment section. Ask your question in the comment section. So still on the ball scenario. So the ball, so I've labeled the part A, B, C. So the ball can be moved in one step from A to C. From A to C. However, it can also involve two steps. And these steps are first from A to B and from B to C. So these two steps, which is from A to B and from B to C, have the same overall effect as from A to C. Meaning if you move from A to C, where the ball will end is the same as moving from A to B and B to C, basically. So the A and B to C are the resolved vectors of the original. So let's pick an example. Maybe that will make sense to you. I think we have just How many examples here? Yeah, we have this one example. Yeah, we have this one example. So here's a question. A body possesses momentum. Yeah, a body possesses momentum of 15 kilogram meter per second and inclined 20 degrees with the vertical. So that's the question. Calculate the vertical component of the momentum and the horizontal component of the momentum. So this question basically means that resolve this original momentum, which is inclined at 20 degrees to the vertical, into vertical and horizontal component. That's basically what it means. So from this question, let's write out the parameters that we have. You can see that we've been asked to find the vertical component and the horizontal component. So let's use some symbols to represent them. So the vertical component, we use my to represent the vertical component. Y like y-axis, the x is x-axis, and the m is momentum. So my and mx. So my represent the vertical component and the mx represent the horizontal component. So we get that given. Now, in the question, we've been given the momentum to be 15 kilogram meter per second. I'm sure you took note of that. Then we also have the angle at which that momentum is inclined with the vertical. So the momentum is inclined with the vertical at 20 degrees. So you can see that the 20 degrees at the top. So it's inclined at 20 degrees. So that momentum, the original one, is the one with the arrow on top. So that's the momentum. And now the question is asking you to split this single momentum into horizontal and vertical. So that's basically the entire idea behind resolution of vectors. I hope that's clear. So look at this diagram. So that horizontal momentum, the original one given the question, is what is referred to as the resultant momentum. The resultant momentum is the overall momentum of the object. So now we are going to split it into the vertical and the horizontal. So how do we go about it? The first part is to split it into the vertical component. So the vertical component, the my. So we label that as my and the horizontal as mx. So the my. Good. So this is where we are going to apply the knowledge of Soh Cah Toa trigonometric ratios. So if you have not watched that lesson on trigonometric ratios, I will advise you to watch it and come and continue with this lesson. Trig ratios. So you are going to use it. The trig ratios are Soh Cah Toa, sine, cos, and tan. Watch that lesson, understand it very well, and then come back to this lesson. Now, if you look at the diagram that I have on the screen, we have 20 degrees at the top, right? That is the angle at which the momentum is inclined with the vertical, 20 degrees. So this is a right angle triangle. So if this is 20 degrees, it means the right angle is 90. And the total angle in a triangle is 180. Good. So the corner is 90, 20. The right angle triangle is 90. That means this corner is 70 degrees. So let's find that missing angle. That gives us 70 degrees. So we found all the angles in the triangle. Now the first part, my. Which of the trig ratios are you going to use? Are you going to use sine, cos, or tan? In this case, you will use sine. We are going to use the 70 degrees. Our focus is going to be on the 70 degrees because we want to find the my, which is facing the 70 degrees. So that's what you'll be using. So let's go. Well, we are not going to spend so much time on the trig ratios because there's a lesson already on that. So in this particular question, you're going to use sine theta is equal to opposite over hypotenuse. The hypotenuse is the inclined one, which is the momentum that has been given, the hypotenuse. And it's given the question as 15 kilogram meter per second. So we know the angle, which is 70 degrees, and then the hypotenuse is 15. We are looking for the vertical, so that's the only thing missing. So sine theta equal opposite to the hypotenuse. Then the theta is 70, so sine 70 equal my, which is the opposite divided by hypotenuse 15. So put in your values. Change of subject, my. So my becomes 15 sine 70, and that gives us 14.09 kilogram meter per second. You can check it on your calculator and see what that gives you. We have the next one, which is the horizontal. The horizontal component, which is the B. For that one, we are going to, we can still use the hypotenuse and then the adjacent, hypotenuse and adjacent, for which of the trig ratios has hypotenuse and adjacent. That gives you, that's us cos adjacent and hypotenuse. So cos theta is equal to adjacent over hypotenuse. I repeat, I have a lesson on trigonometric ratios. Watch that lesson first. Yes, watch that lesson. I'll leave the link to it in the description. Watch it, and this, all of this will make sense. So cos theta equal adjacent to the hypotenuse. The theta is 70 degrees. So cos 70 equal mx, which is the adjacent, divided by hypotenuse. So making mx the subject, mx equal 15 cos 70, and that gives us 5.3 or 5.13 kilogram meter per second. So what we basically did now is that inclined momentum that we were given, we have resolved it into its horizontal and vertical components. Keep that in mind. We have resolved it into its horizontal and vertical component. So these are the steps involved. I hope that makes sense to you. If you find this lesson helpful and understandable, give it a thumbs up and subscribe to the channel anyway. See you in our next lesson.